Hey guys, so this will be the last lesson here in our vector dynamics lesson. It's going to lead straight into torque and static equilibrium. So this last lesson here is also called static equilibrium. We're going to start first by not with this first example, but by going back and looking at this problem here, this static equilibrium problem, and we're going to launch into the bigger, badder ones in the lesson 9. So there's a couple ways we can look at this kind of problem. Now, a static equilibrium problem means, well, static means the thing's not moving. The object is at rest. What that means is, if the object is totally at rest, you've got to have balanced forces, and in this particular example, now that we're dealing with 2 dimensions, this is true for the horizontal forces as well as the vertical forces. Everything has to be balanced. So there's actually 2 ways you can deal with this. You can use the vector sum of forces, or I'm going to do, and I'll show you what that looks like in a second here. The other option I'm going to put on the side here too, I guess I could have started left to right, but whatever, I'm going backwards, is by balancing the vector sum of forces, or you can use components. Okay. Look at the vector sum of forces. If the vector sum of forces are balanced, that implies that the vector sum adds to 0. And when you're adding vectors together and they add to 0, what that means is the vectors loop around on themselves. I'll say it that way. That'll make sense here when I do some drawings here in a second. So if I look at this thing here, I've got a cable 1, I've got a cable 2, and I've got an object hanging here. I'm going to add my forces, I'm going to make my free body diagram. I've got Fg acting downwards. I've got a tension. I'll call it force of tension in cable 2. And then I've got the force of tension here, Ft in cable 1. Now, if the vector sum of the forces equals 0, what that means is this. So if I'm going to add up, I've got force of tension 1, force of tension 2, and gravity, and I'm going to add them up like we add up vectors. So I'm going to draw them tip to tail. So I'm going to have F1, actually, I'm going to do all of this in green. So I've got my force of tension 1. I've got my force of tension 2. And I got Fg. And now when they add up, the vector sum adds to 0. These 3 vectors added together, I should end where I started. And where we started. There is no resultant then in this case. The sum is 0. And then this gets relatively easy. We can see what's going on here. I've got this angle here. Oh, I shouldn't use that color. I'll use red. I've got this angle here is 35 degrees. Well, that 35 degrees is off of a vertical, but Fg is vertical. It's straight down. So I know that this guy here is 35 degrees. They don't tell us what the angle is in here, so the implication is that this is actually a 90. That cable 2 is going perfectly flat. So if that angle there is a 90, that means the angle, but if I just slide this over, that means the angle between Fg and cable 2, this guy here has to be 90. And so now by doing our vector sum, drawing it out this way, I can use basic trigonometry to figure out what F1 or Ft1 and Ft2 have to be based on the fact that we know what Fg is. We know that Fg is 9.8 times 10, which is 98 newtons. So this becomes really quite easy to solve. Alternatively, we can break this thing up into components. This guy will have a force of tension 1 y component and the force of tension 1x component. If I'm balancing components, what I have to have here is that my sum of my left have to equal the sum of my right, and the sum of my upward forces have to equal the sum of my downward forces. And this is relatively easy. That means that force of tension 1x has to equal F force of tension 2, because this one's to the right, no, it's to the left. And then if up equals down, that means my force of tension 1y component, tension 1y component, is going to have to equal Fg. Well, then we know that this is 98, then we can use trig to find T1x, and then we know that T1x has to equal cable 2, and then we're done. So there's two different ways you can approach a question like this. I want you to practice a couple of them in the homework that I give you, but before I do that, I want to go through some of the really gross questions out of lesson number 9. So flip back now to this lesson here. Static equilibrium. Now, these guys are going off at all sorts of weird angles. We can solve them, though, the same way that we've been solving these guys here already. Now, there are two ways we can handle this. We can use components or we can use vector sums. I'm going to show you the vector sum route, and I'm going to show you the components route. So I'm going to leave some space here. We're going to draw, we'll use orange. Yeah, let's do this. Let's draw the line right here. That should be enough space. We're going to do vectors over here. And we're going to do components over here. Okay, I'm going to show you the component method first. Now, if we draw this thing out, if this thing is static, it means it's not moving, and the implication there is the first thing we need, the first thing we need to recognize is this. One, that my vertical force components are balanced. And two, my horizontal force components are balanced. Okay, so what are these components? Let's draw them in here. So I'm going to do, I'm going to do this guy here in pink. This is cable 1. This guy's going to do in green. Here's cable 2. And so this guy's going to have a component that goes this way. And he's going to have a component that goes that way. This guy is going to have a component that goes this way. And he's going to have a component here that goes this way. Okay? I'll label what these are. I'll try to keep it clean. I'll call this force of tension 1y. And this is going to be force of tension 1x. Here's my force of tension 1. This is going to be my force of tension 2. So this is going to be Ft2y. And this is going to be Ft2x. Okay? So, using 1, vertical components are balanced. Actually, no, let's not set it up that way. I'm going to use a T-chart like before. Something that you've seen, similar to how we set up kinematics. So we had horizontal, and we had vertical. Okay? So using horizontal and vertical, if I've got right, let's do the horizontal ones first. Oh, no, I forgot to draw one more thing on here. We've got Fg acting downwards here, and Fg we know is 1,176 newtons. The 120 kilograms times 9.8. Okay, cool. So horizontal components. I know that force of tension 1x has to equal force of tension 2x. I also know vertically that force, I've got 2 acting upwards, so their sum, force of tension 1y plus force of tension 2y has to equal Fg. And I can start putting some values in here. Now look at this. My force of tension 1x, this is the 40-degree angle here, that's the 10-degree angle there. So F of T1x is going to equal F of T1 cos 40. So this is going to be F T1 cos 40, and this is going to be F T2 cos 10. That's as far as we can go at the time for the time being. This one is going to be F of T1 sine 40. Looking at this triangle here, that's opposite. So we're going to use sine plus F of T2 sine 10, and that sum is going to equal 1,176. Now I've got 2 equations, 2 unknowns. I can take one, I can substitute it into the other. Okay, so what I'm going to do here is I'm going to solve this one because it's simpler, and I'm going to substitute it in here into the other one. So I'm going to have F of T1 is going to equal F of T2 cos 10 over cos 40. And I'm going to substitute that in right here. So I'm going to get force of T2 cos 10 sine 40 over cos 40 plus F of T2 sine 10 equals 1176. Okay. Cos 10, sine 40, and cos 10 are just numbers. I can multiply those 3 things together. And what I'm going to get here is I'm going to get this expression. I'm going to get force of tension 2 times, what is that? 0.82635. I'm going to keep 5 decimal places on that just to reduce my rounding error. Plus, now sine 10 is just some value, so it's going to be F of T2 times 0.17365 equals 1176, which is going to give, if I solve for this thing now, I can actually see that these two are going to add up to 1. So this is going to add up to FT2 is going to equal 1176. Well, isn't that interesting? So the tension in T2 is actually equal to the mass downwards here, or sorry, the weight downwards here. Now we can go back and we can substitute that back into our previous equation here for T1. So I've got F of T1 is equal to 1176 cos 10 over cos 40, and I find that F of T1 is equal to 1,511.84 newtons. There's my tension 2. There's my tension 1 using a component method. Okay? Relatively easy, nice and straightforward. Now I'll show you what that same thing looks like here using the vector sum. What I'm going to do is I'm going to draw these guys up here, and I know that this guy plus this guy plus this guy has to loop back in on itself. So we're going to get something that looks like this. We're going to get, so I'm going to keep them the same color here, that pink guy there plus this green guy here has to equal this red guy here. These guys have to add up. And the only value I know here is that this is 1176. Now I can use what we know about angles. So we know, I'll do some drawing in here. I'm going to add some some coordinate grids. Okay, we know that this angle here is 10 degrees. So we know that this angle here is 10 degrees. Now, using the angle stuff that I had you guys look at before, alternate interior angles, these two west and east here are parallel, which means this angle there has to be 10 degrees. Okay. I should zoom this in so it's easier to see. So that angle there is 10 degrees and this angle here is 10 degrees. Now, this angle here is 40 degrees and it meets with a horizontal. So this vector, as it goes up in here with east here, is going to be 40 degrees. And this down here is going to be 40 degrees, which is going to make this entire angle here 50 degrees, which is going to make this entire angle here 50 degrees, because that's a 40. A 40 and 50 is 90. And that's going to make this angle up here 80 degrees. Now, I haven't drawn it properly because that angle is bigger than 40, but look at what we have here. We've got a triangle where the two angles here are the same. It means this is an isosceles triangle. Means opposite sides, or opposite sides equal angles are equal. So that means that this side here has to be 1176, and then we can use cosine law to find that guy there. Or we could use sine law. I guess it doesn't really matter. But we get the same value moving forward here. So I could just say use sine law to find that guy there. So we can use the vector sum relatively easily. It's important to remember, though, and I've said it once, I'll say it again, for an object in equilibrium, forces begin and, or I'll say the sum of the forces, I should say that, sum of the forces begin and end at the same spot. So two equally valid ways to approach a question like this. Again, I said it before, I'll say it again. The conceptually simpler way to deal with this is components, but there's a lot more math involved. Math isn't hard, it's basic algebra that I teach in my grade 9s. The conceptually more difficult way, that uses slightly more advanced mathematical reasoning, is the vector sum methods, but the work is arguably much, much simpler. But yeah, I'll do one more example, and then that's it for this lesson. You guys can go on and play with these questions after that. So flip the page. We're going to have a question that looks like this. I've got a mountain climber hanging on a wall. There's a rope acting here. We're told that to assume that the climber's feet are tending to slip downwards, so that friction must be upwards, and the climber himself is at rest, or herself is at rest. Okay? So let's free body diagram this thing. We're told the climber's at rest. All the forces on this person. We've got Fg downwards. We've got force of friction upwards. We've got a tension in the rope. I'll put it here, force of tension. And there has to be another horizontal force, because this guy, if we look at what's going on here, if I choose to break this thing up into components, here's my components, F of Ty, F of Tx. I can see that there's a horizontal component here, so there must be another horizontal force that we're not considering, which means, and this guy is on a surface, so there has to be a normal force acting off the wall. So that's my free body diagram. We know that the force of gravity is equal to 650 because they tell us that right there, 650 Newton climber. And now we can go forward from here. So I want to write out my implications again, but I'm going to do it a little bit sloppier. We know that this thing is in static equilibrium. Maybe not sloppier. I'm going to do it a little bit more condensed. So if I'm in static equilibrium, that means the sum of my leftward forces or components equals the sum of the right. And that the sum of my upward components equals the sum of my downward components or forces. So for this one here, because I've got more than 3 forces, they will draw nicely if I, played with it properly, but I'm not getting nice triangles because I'd have 4 forces here drawn together. I'd have this guy that goes up at an angle, and then the one goes up, and the one goes over, and the one straight down. I'd have some weird looking shapes. You could do it. It would be doable, but I'm not going to. I'm going to use components for this problem. So the sum of my leftward forces, I've got one component or one piece of a force acting to the left. That's Ftx. So I'm going to have Ftx, and I've got one thing acting to the right, and that's my Fn. We're told that that angle there is 8 degrees, so that means this angle here has to be 8 degrees. So Ftx is going to be Ft sine 8 equals Fn. That's as far as we can take my left and right. Now we're going to go work on up and down. My sum of my ups and downs, I'm going to have Fty plus my force of friction, which we're told is acting up, is going to equal Fg. Well, what do we know? We know that force of friction is equal to mu Fn. And we know that Fy is going to equal Fty is going to equal Ft cos 8. So I'm going to have Ft cos 8 plus 0.65 Fn equals 650. Well, I've got Ft sine 8 equals Fn. This is already solved, so I'm just going to take that and I'm going to substitute it in over here for Fn. What that's going to give me is that Ft cos 58 plus 0.65 Ft sine 8 equals 650. Yep, these are just all numbers. You can multiply 0.65 by sine 8. If you do this, you're going to see that Ft is going to equal 601.44 newtons. So then we're just going to take that and we're going to shove it back in there for Ft. So that Fn then is going to equal 601.44 times sine of 8, which is going to equal 83.7 newtons. So I've got a value for Ft, which is equal to 601.44, and I've got a value for Fn, which is 83.7. Both of those should be measured in newtons. And we're done. Relatively straightforward as long as you follow the procedure. Looking at forces balanced left-right, forces balanced up and down, and then the implications of what that means. So I'm going to leave you with the homework here. If you flip the page, you guys, here's what I want you to do. I want you to look back at page 130 and do number 10. That's from lesson 8. And then I want you to do page 135, numbers. I want you to do number 1. I want you to do number 8. Did I skip one? Oh, I did skip one. Sorry. I want you to do number 1. Sorry, let me rewrite this. 1, 5, and 8. Careful with number 5. Number 5, there's a lot going on there, but make sure you read the questions, figure out what it's actually asking you to do. You're just drawing force diagrams and writing net force equations. You're not actually solving anything. So you're just setting them up. So I want you to do 1, I want you to do 5, and I want you to do 8. So there you go. Tomorrow we'll be starting torque, which is an entirely new concept, but it builds on these ideas of forces in equilibrium. Torque just makes things spin. So there we go. And then we'll come back and we'll do the unit 3 after that. As always, if there's any questions, please let me know.